Hello everybody. Welcome you all to the next session regarding discussion on the problems with respect to the introduction of turbo machines part. So already in the previous sessions, we have studied regarding the significance of the various pi terms, where we have discussed the significance of the head coefficient, then discussing regarding the power coefficient, flow coefficient, specific speed of a pump of a turbo machine. Similarly, the various unit quantities such as unit flow, unit speed, as well as unit power. In today's session, we'll be discussing some of the problems related to all of these. So as we move further in this particular session, we'll be discussing some of the questions which are asked in the previous question papers and how you can get the solutions using these particular things related to the unit quantities and the related pi terms. So let us see the things one by one. So if you have any doubts, you can see my email IDs here, which I have already written here. Along with that, even you might send my mobile WhatsApp number also. You can email me or send me on WhatsApp, through which I can clarify your doubts. Okay, students. So now we shall move to the part one by one. So now, before we move to the discussion of the problems, let us have a glance regarding the terms, that is the specific speed of a pump as well as a turbo machine, then the unit quantities. So a specific speed of a pump, how we are writing this one? We are writing it as Ns is equal to N root Q divided by S to the power of 3 by 4. Whereas for a turbo machine, that is for a turbine, we are writing it as N root of P divided by S to the power of 5 by 4. That is the only difference. That is, this is for turbine, N root P divided by S to the power of 5 by 4. Similarly, for unit quantities, if it is an unit flow, we write it as QU is equal to Q divided by root of H. Whereas if it is another term known as unit speed, that is Nu is equal to N divided by square root of H. Similarly, unit power is given as Pu is equal to P divided by H to the power of 3 by 2. So many times in the examination, we have some confusions. So please do remember these simple equations very easily, avoid confusions. Only thing is, when we are writing specific speed of a pump, the parameter here is Q and the H value power is 3 by 4. When you are writing with respect to turbine, we are having parameter as power P and the power of H as H raised to 5 by 4. The same here also, for both unit flows and unit speed, we are having square root of H itself. But if you come for unit power, the value is H to the power of 3 by 2. Please do remember these differences, such that you won't commit any mistakes when you are solving the problems. So let us move further regarding the discussion of the questions which they have asked in the previous question papers. Now the first question which you can see here is, it has been said that there are 4 turbines. There are 4 turbines of a specific speed, 890 metric. Each is installed in a idle station. Each of turbines runs at 50 RPM, which share equally a total discharge of 260 meter cubes per second, which is available under a head of 1.73 meters. Where you have to assume each turbine has an efficiency of how much? 82.5%. Find the power of each turbine in kilowatt. This is the question given to you. So if you extract the given from this particular problem, the first thing here said is, how many number of turbines? We have 4 number of turbines. So the 4 turbines is, its value is N is equal to 4. Next, specific speed 890 metric. What it means that the specific speed Ns, which is 890, it is in terms of metric. Ns is equal to 890. It is in terms of metric. So metric means MKS system. So you need to convert this back to which system? SI system. So we have one conversion factor. If you use that conversion factor, you can convert from metric to SI of the specific speed. Similarly, next he has said that these turbines, in that each turbine it is running at a speed of how much? 50 rpm, which means that is n, capital N speed. All together share a total discharge of how much? 260 meter cubes per second. He has said total discharge, which means it is Q suffix T, total discharge. And these are operating under head of how much? 1.73 meter, which means it is H. Assuming each turbine has an overall efficiency of how much? As 82.5%. You need to find what? Power of each turbine. These are the things you need to find out when you are solving the problem. So now let us go step by step. The given data. As I said, the number of turbines is 4. Head available is 1.73. Specific speed in matrix is 890 matrix. Efficiency 2.5%. Then your speed is in 50 rpm and the discharge it is a 260 meter cube per second. So you can say this as this particular thing. So now I told you the important thing is if it is given in matrix, you need to convert it into SI system. So for conversion to SI system, this conversion factor is needed for specific speed. That is, if you multiply the specific speed of metric with the conversion factor 0.857, then you get the value of specific speed in SI units. So in SI units, we get the value as, let us see what we get the value. We get it as 762.73, and this is a dimensionless case. Specific speed, it is a dimensionless number. It is just a number. It is a dimensionless. Then for turbines, you know the specific speed equation. If you are using, we write it as ns is equal to n root p divided by h to the power of 5 by 4. Speed is already given in the question. That is 50 rpm. Specific speed just now we have calculated. Even head is given. So what we can find out? We can find the power P. So the power P, if we substitute all these terms, the power P, we get it as how much? 916.030 kilowatts. Similarly, we need to find even the efficiency also. So now this efficiency term, how do we find out? We found out this efficiency term as this, we need to write it as overall efficiency or turbine efficiency, no problem, because the further equations I've taken it as efficiency not, no problem. You can use that one, or you can come with the this thing also, that is this particular part. So now actual power, yes, I was telling you, it is P actual is equal to P into efficiency not, or what you can do is you can have this as I was telling you, the efficiency, you can write term it as efficiency not, as I have taken it as all the overall efficiency, no problem. You can keep it or you can leave it also. So what do we get? Actual power is equal to the power what we have got. It is having some, the turbines are 82.5% only efficient. So we need to consider that efficiency factor also. So once you consider the efficiency factor, we get it as this value. This is the value which we are going to get it as 755.724 kilowatt. This is for one turbine. If you are having 4 turbines, multiplying it by 4. So the resulting, how much we get? The total power output, we get it as 3022.896 kilowatt. This is the answer for this particular problem. Similarly, the next question, here you can see they have said that there is a quantity of water available for a hydel station is 310. This term we call it as cubic meters second. Cubic meter second we call it as, and it is having suffering under present under a head of 1.8 meter. Assuming speed of at each turbine is 60 rpm with an efficiency of 85%, find the number of turbines required and power produced by each turbine. Each turbine has a specific speed of how much? 800, again in metric here itself. So here also, if you go for noting down the given data one by one, You can see that there is a quantity of water available in a idle station. So idle station means it is a hydroelectric power plant. And he has said a quantity of water available. Quantity of water available means it is Q itself. How much he has said? He has said it as 310 cubic meters per second. CUMECS. It is also known as cubic meters per second, or this you can write it as 310 meter cube per second. 310 meter cube per second. You can write it as. Then he has said that there is a head of how much? 1.8 meter, which means H. This is the value of H. Then he has said it is a speed of RPM, means here each turbine, it is having a speed of how much? 60 RPM. Efficiency it is eta, that is 85%. We need to find out what? How many number of turbines are required to operate this idle power station. Along with that, we need to find out the total power as well as the power required by each turbine. So how many number of turbines and the power required for each turbine. He has given another one term, that is specific speed, NS, but it is given in terms of metric. We need to convert it into SI by using the conversion factor which we have discussed in the previous problem. Let us see the things one by one. So this is the given data which we have written now here. Now, conversion for the specific speed, NS is equal to, I told you the conversion factor is used is 0.857. This is the conversion factor. So if you multiply the 0.857 conversion factor for the NS specific speed in the metric value, we get the resulting values in terms of the SI units, the values of SI units. So the value of specific speed in terms of SI is 685.6. So now the total power, first we need to calculate. The total power is calculated using this equation. P2 is equal to rho GQH n eta naught divided by 1000. Here the power which you are going to calculate, it is in terms of kilowatt. That is the reason that we divide this equation by 1000. The power which we are going to determine, it is in terms of kilowatt. That is the reason that we divide here it by 1000. Then density rho, as you have told that it is the fluid is the water itself. So standard value of density of water is 1000. You know the value of G 9.81. Q, it is already given in the question. That is the value of Qt. You can say you can take it as Qt itself here also. It is how much? 310 meter cube per second. H is also given to us. Eta naught is given, so you can calculate the total power of a, which is missing. We need to calculate total power of a power plant. So let us see what are things we are going to get now here. So once you substitute the values, the total power you are going to get it as 406.52.883 kilowatt. This is for the total entire power plant. The question asked to us is we need to calculate the power for each turbine and how many number of turbines are required. So now let us go for calculation with the power required for each turbine. Even you can calculate with the help of the specific speed equation also. So let us say the specific speed equation, I write it as NS is equal to N root P divided by H to the power of 5 by 4. Specific speed, just now we have calculated in the form of SI units. N is already given in the question. H, just now we have, it is also given in the question. Then whatever the value of P we get, this value of P power, it is for each single turbine. Total power for the entire power plant we have calculated, that is using all the turbines together. Now once we substitute all these values here, we get the value of power for each turbine. It is how much? 567.57 kilowatt. Now using the total power of a idle power plant as well as the power of each turbine, we can find out how many number of turbines are required to generate the power. That is, number of turbines is equal to PT is equal to N into P. If we substitute, we get the value as N is equal to 8.19. So 8.19, we need to round it off. So better is, you can say approximately around 9 turbines are required. Approximately around 9 turbines are required to generate the power from a idle power plant. This is regarding this particular problem. Similarly, another problem. Here in this problem, he has told that there is one Pelton wheel which is running at a speed of 200 rpm and it develops 5200 kilowatt with a head of 220 meters, having an overall efficiency of 80%. Determine its unit speed, unit flow, unit power, and specific speed. Then find the speed, flow, and power when its operating point changes to a head of 140 meter. Take density of water as 1000 kg per meter cube. So if you read this problem carefully, this problem has two parts. The first part, for it starts from here itself, Pelton which is running at a speed of 200 rpm, which is developing 5200 kilowatt power. Head has 220 meters. Overall efficiency is 80%. With these conditions, we need to find what? Unit speed. Unit speed in the sense that is n suffix u. Unit flow, that is qu. Unit power, pu. Specific speed, ns. This is the first part of the problem. Up till here, this is the first part of the problem. Second part of the problem is, if you read a question carefully, again, we need to find speed, n, flow, that is q, power, p, when its operating point changes to a new value of h. So for the second part, what is the value of h? You can see it is 140 meter. Initial case was how much? It was 220 meters. So now, if initially h1 is 220 meters, in the second case it is h2. The value is 140 meters. So for this value of 140 meters head, you need to find the value of power p2, speed n2, flow q2. So as I told, we are having two cases in this problem. So we need to solve first each case one by one separately, such that we can get the required results. Let us proceed. First, note down the given things. So for given things, for the first case, he has said 200 rpm is there. Speed, power developed is 5200 kilowatt. Head developed is 220 meters. Efficiency of 80%. And apart from that, the density of water is 1000 kg per meter cube. Let us find the unit speed. Unit speed equation we know, nu is equal to n1 by root of h1. Already we have discussed this equation, and also we have glanced today before beginning of this particular session, that is nu is equal to n1 by square root of h1. n1, it is available here, h1 is available here. We can find out unit speed. Similarly, you can find even unit flow, unit power, as well as specific speed. Let us proceed one by one. So solution, unit speed is given by nu is equal to n1 by square root of h1, or if you substitute the values here, we get the unit speed as 13.483 rpm. Similarly, for unit flow, qu is equal to q1 by square root of h1. But the thing here is, we don't know q1. We need to find q1 using our power equation. Power equation, p1 is equal to rho g q1 h1 efficiency naught divided by 1000. Power p1 is given, rho g we know, q1 we need to estimate, h1 is also given for the case 1, efficiency is also given. So this is the missing term. We need to find q1. So to find q1, we use this power equation. So once you substitute the values, we get the value of q from this equation, that is q1 is equal to, substitute the values, the value of q1 we get it as 3.0117 meter cube per second. Now the unit flow qu is equal to q1 by square root of h1. Substitute the values, you will get the value of unit flow as 0.20305 meter cube per second. Similarly, unit power, only difference is here now the power of h1 becomes 3 by 2. The power of h1 becomes 3 by 2. So if you substitute the value, what do we get? 5000. If you get the value, the unit power value is 1.5935 kilowatt, 1.535 kilowatt. This is the case. Another term which we are left is the specific speed. So now as we are having both discharge and power, you can use any of the terms. So already you know when we are calculating the specific speed, we are having two types of equations. We can go, the best equation I say is Ns is equal to N root of P1 divided by H1 to the power of 5 by 4. Use this particular equation, get the value of Ns. Let us see how much value we get now. N1 root of P1 divided by H1 to the power of 5 by 4. The specific speed value, we get it as 17.021. This is regarding case 1. In case 2, what he has said that he has shifted the head position. The head position, initially the first case, H1 value was 220. Now for the second case, the S2 value, what he has done, he has decreased. So the second case, S2 value, it has been decreased to say around 140 meters. So for this particular height of 140 meters, we need to find P2, N2, we need to find Q2, P2 and other things. So let us see how we can get the solution for this particular second case now. So case 2, I said we have written the conditions of the first one, that is along with that. For the second case, only the given things is he has given only the head. For the second case, he has given only the value of head. That is, this particular part is with only the respect to case 2 in the given data. Now with using this one, we need to find N2, Q2, P2. In the discussion of unit quantities, I was saying is the terms that the unit quantities which you are discussing, that is, it may be with respect to Q, or that is the speed flow, or with respect to power. There is one term which has to be taken into thing is all unit quantities are geometrically similar. They are geometrically similar. This is the word I had said in each of the definitions. They are geometrically similar. So when they are geometrically similar, what you can say that unit flow QU for first turbine or first pressure is Q1 by square root of H1. Then according to the definition, geometrically similar means definitely this unit flow QU should be equal to Q2 by square root of H2. The same even for unit speed as well as for unit flow also. So again, what you can say that if there is unit power, or say if I am having unit speed, Nu is equal to N1 square root of H1 is equal to, for second engine it is also N2 divided by square root of H2, because they are geometrically similar. Not only we are using these unit quantities. N1, it is already given in the question to you. H1 is also given to you. H2 is also known to you. Only the missing term is N2. So you can simplify it as N2 is equal to the terms N1 by root 1 H1 into root of H2. You will get the value of N2, similarly Q2, similarly Q2 also. Let's see how we are going to get these things. So initially unit speed is same for a machine as we have said, under operating at the same operating at another operating point also. That is Nu is equal to unit speed Nu is equal to N1 by root of H1 is equal to N2 by root of H2. So already we know these things, only N2 is missing. If you substitute the values, you get the value of N2 as 159.54 RPM. The same we do even for the unit flow also. Unit flow QU is equal to Q1 by square root of H1 is equal to Q2 by square root of H2, where on substitution the value of Q2 we get it as 2.4011 meter cube per second. Similarly now for unit power PU is equal to P1 upon H1 to the power of 3 by 2 is equal to P2 by H2 to the power of 3 by 2. So the unknown term is which one? We have P1, we have P2, we have P1, we have H1, We have H2. The unknown term is P2, which you can estimate now. So therefore, P2 is equal to, we get it as P1 into H2 by H1 whole raised to 3 by 2. On substituting the values, you get the value of P2 as 2639.74 kilowatt. So here also, this is the power. Then similarly, if we check here the value of specific speed, what do we get here? Ns is equal to N2 root of P2 by H2 to the power of 5 by 4. If you substitute the values, you will get the same value for the first case. As I told, it's a dimensionless number. So Ns value on substitution, you get it as 17.021 itself. So these are some of the problems which are related to the specific speed. These are some of the problems which are related to specific speed, as well as they are related to the unit quantities. So these are some of the questions which are asked in the previous question papers. Similar kind of questions, you can solve them from any of the textbooks or the previous question papers. If you have any doubts, you can send me an email or WhatsApp, which you have already seen on my first slide at the starting of the program. Thank you, students. We shall stop the session today here itself.